Okay guys, so here is a video where I will go over the basics of game theory. First, I'll talk you through a simultaneous move game where both players reveal their strategy at the same time. Remember, these games are pretty unrealistic in the real world. The only one I can really think of is rock, paper, scissors, and the prisoner's dilemma that we played in class where you revealed your cards at the same time. But when the players are revealing their strategy at the same time, we use normal form, this little window pane looking thing. And we solve these games using the idea of dominant strategies and Nash equilibria. And then we'll talk about sequential games. So this is where one player has the ability to move first, and we represent the games using a decision tree, and we solve using backwards induction. So first, a simultaneous move game in normal form. So let's talk about the battle between friends. This is a game that was originally called the Battle of the Sexes. Here we're going to talk about two friends, Abby and Marie. The first thing that a game needs is players. The two players in this game are Abby and Marie. They have two different strategies. They're choosing if they want to go to brunch or a hike. And they have different payouts, which are going to give them different levels of utility, depending on which outcome they settle on. Say that Abby is player one. She's choosing brunch or hike, and she really likes hiking. So if she goes hiking with Marie, she gets a 5. Say that's pretty happy for Abby. We don't know how happy of a person she is. Marie is also choosing brunch or hike. She's player 2. She doesn't really like hiking, but she likes being with Abby. So if they go hiking together, she gets a 2. Now Marie really loves going to brunch. She's one of those people that reads up on the hottest new brunch place. And Abby, not so big of a fan. She hates waiting in line, and hipster cocktails don't really do it for her. But she does like being with Marie. So we have to assume about what happens when they go and do different things, that they like being together more than they like doing the thing that they don't enjoy as much. So that means that if Abby goes for a hike and Marie goes to brunch, Abby is not as happy here as she was when she was getting to go to brunch with Marie. So she doesn't really like hiking alone. And similarly, Marie does not really like going to brunch alone. You would get a totally different outcome of the game if you assumed that Abby likes hiking more than she likes Marie. If Abby goes to brunch and Marie goes hiking, that's really terrible for both of them, because they're doing the thing that they don't like, and they're doing it alone. So let's say they both get -5s. So that's the intuition for this game. Two friends, Abby and Marie, who enjoy being together more than they enjoy doing the thing that they love, and they're trying to coordinate their actions. So first thing that we're going to do is check for dominant strategies. What a dominant strategy will look like in this game for Abby is a row where the blue is always higher. Does she have a row where the blue payout is higher in every column? So for example, in the column of brunch, Abby going to brunch is beating hiking. 2 is better than 1, but -5 is worse than 5. So there's no row where Abby is always better off, because what she's better off doing depends on what Marie does. So there's no dominant strategy. None for Abby. For Marie, we're thinking about her own strategy and her own payouts. So it's a column where the green is always highest. A strategy where, independent of what Abby does, she's better off. 5 is better than -5, so far brunch is winning, but 1 is worse than 2. So there's no column where she's always better off. So again, she also has none. A lot of the games we've looked at, this is true. where one player having no dominant strategy means the other will also have no dominant strategy, but that's not necessarily always the case. You could have one where one player has a dominant strategy and the other does not, like the Rock Shop and Me Tunes example we did in class. Now we're going to check for Nash equilibria. Remember, Nash equilibrium is different from a dominant strategy because in Nash equilibrium, you think about what your opponent is doing. Here, this was a strategy that was best for them, regardless of what their opponent did. Now we're going to think about a strategy that depends on what your opponent is doing. So for Abby, when we check for Nash equilibria, she's going to look within a column. She's going to look at Marie's strategies and pick the best blue payout. So her rival strategies, but still her payouts. So for dominant strategy and Nash, Abby only cares about blue. But for Nash, she cares about columns instead of rows. So for Abby, if Marie goes to brunch in this brunch column, Abby will choose to go to brunch as well because 2 is better than 1. If Marie is brunching back is Abby's best move, right? She doesn't like hiking alone. If Marie is hiking, Abby could get a -5 by going to brunch. Her best move is to hike back, right? She wants to coordinate. So if Marie's hiking, hiking is her best move. For Marie, when we check for Nash equilibria, we're looking for a column, Marie's going to look within the rows, her rival strategy, and pick the best green payout. Another way of saying this is she's looking for her best response to her rival's move. So if Abby goes to brunch, should Marie get a 5 and go to brunch as well, or get a -5 and go hiking? A 5 is her best response, which means we found a Nash equilibria because they're both underlined. But we'll talk about that in a second. If Abby hikes, would Marie like to get a 1 or a 2? She would like to get a 2, right? If Abby's hiking, Marie does not want to go to brunch alone. She wants to hike with Abby. So there's actually 2 Nash equilibria. A Nash equilibria is one place that both players are making their best response to the other person's move. So neither has any incentive to move. So we have 2 Nash equilibria. Brunch, brunch, and hike, hike. This is pretty similar to the game of stag hunt that you guys did on your homework, except there is one equilibrium that is better for one of them. Hiking is better for Abby, and brunch is better for Marie. Unlike stag hunt, where stag was better for both of them, and hare was worse, right? But it's a coordination game where they want to do the same thing as the other person. Another way to check for Nash equilibria is to go square by square and say, does anyone have an incentive to move from this place? So from brunch, given what Marie is doing, Abby does not want to move and lose 1 point. Marie does not want to move and lose 10 points. So this is stable. Hike is unstable because Abby would like to move and gain 10 points by hiking if Marie's hiking. Marie would also like to move and gain 10 points by going to brunch if Abby's going to brunch. This is not a stable point. People want to move out of it. If they are here at hike, Marie does not want to move because she'll lose 1 point by switching to brunch. Abby does not want to move because she'll lose 10 points by switching to brunch. So they stay here. This is a stable place. This also unstable because Abby would like to switch to brunch if we're here, and she can move us to there. And this is unstable because if Abby's hiking, Marie would like to gain a point by switching to hiking back. Okay, so that's Nash equilibria and dominant strategies. Dominant strategies, we had none. Nash equilibria, we had 2. So that was a simultaneous move game. In the context of 2 friends deciding what you could do, you could think about that as the pre-smartphone, pre-cell phone, pre-email era. So these friends have to make their decision about what to do without being able to contact each other in the moment. So they're just like, let's meet up after class, and they go to a location where they think their friend will be. The idea is they will coordinate on brunch or hike, but we're not sure which is more likely. 2 equally likely Nash. Now, we're going to talk about the same game, but we're going to have a sequential game. let's say that Abby wakes up first. She's an early riser, so she has the first move. She can either go out for a hike and tell Marie that she's hiking, or she can get in line at a brunch place. And then Marie is going to observe Abby's move and be able to make her decision given what her friend is doing. I'm just going to try and have this be in the picture as well. Let's see if I have the technical skills to zoom out a little bit, so you can see the original game while I'm drawing the sequential game. So here, this first node, this is Abby's decision. I'm going to read left to right. Abby is choosing brunch or hike. The second node, this is Marie's decision. In the world where Abby has brunched, Marie can either choose brunch or hike. I'm just abbreviating. And if Abby has gone hiking, Marie can choose brunch or hike in that situation. If they both go to brunch, Abby gets a 2 and Marie gets a 5. So this is just the brunch box from up here, 2, 5, 2, 5. If Abby goes to brunch by herself while Marie is hiking, that's a -5 and a -5 because they're both doing the thing they don't want to do and they're doing it alone. And if Abby goes hiking while Marie goes to brunch, that is, again, they're alone, but at least they're doing the thing that they like to do. And if they go hiking together, that's the spot that's best for Abby and kind of neutral-ish for Marie. She's with her friend, but not doing what she wants. So that's how we take this simultaneous move game and turn it sequential. It's easy because Abby was the first player and she got to go first in the sequential game, so you list their payoffs in the same order. Now the way we solve these is using backwards induction, which means we start at the last node. So we start at the end of the game and we say what Marie will do. If Marie is at this decision point and she sees Abby go to lunch, she's choosing between going to brunch back and getting a 5 or going hiking and getting a -5. So this branch will never happen. And she'd never willingly get a -5. If Marie is at this node and she can go to brunch and get a 1 or go hiking and get a 2, seeing that her friend is going hiking, she will always choose the 2. So this branch will never happen. We know we're going down the hiking branch if Abby goes hiking, and we're going down the brunch branch if Abby goes to brunch. That means that Abby is making her decision with full knowledge of her friend's preferences and response. Abby knows if she goes to brunch, she'll get a 2 because Marie will be there. If Abby goes hiking, she'll get a 5 because Marie will see that she's hiking and she wants to be with her friend more than she wants to go to brunch, so she'll come back. So Abby chooses the 5 over the 2, and this will never happen. So now there's only one Nash equilibrium, and that's hike, hike. Abby has a first mover advantage because she was able to eliminate this Nash equilibrium of brunch, brunch, which was less optimal for her, and move it so that there's only one potential outcome to the game, where she's getting to do what she wants with her friend. Marie have any incentive to commit in this strategy? Yes, she does. If she can somehow commit to brunch so that Abby doesn't believe this is possible and this is possible. Like what if Marie burns her hiking shoes or breaks her leg? That would be big time commitment. Hiking is no longer an option for her. That means Abby knows Marie is going to brunch no matter what. She would be choosing between getting a 2 and a 1, and that would make this Nash equilibrium possible again. So Marie does have an incentive to commit and to cut off her hiking option, tie herself to the brunch mast, if you will. So that's commitment, first mover advantage, and how we solve these sequential games. Hopefully that makes sense. We can do lots and lots of random games together and just put 4 boxes together and quiz yourself. I hope you're having fun studying.